Nguyen. I'm the Dean of the School of Engineering. It's great to see you all here. So we're delighted to host the second Ricci lecture. We have Steve Ricci and his wife Geraldine in the front row here, and I'll introduce them a little later, but it's through their generosity that we're able to give this Interdisciplinary Research Prize and to host this lecture. So I hope you enjoy it. The concept was to have teams of students working on a prize that furthered research from the faculty and was interdisciplinary in its context. And all of you are probably aware that the prize is $5,000 for the first place winners. And we're happy to host those first place winners today. We have 2 of the 5 team members who won last spring. And I guess you all graduated, right? Yeah, which is a big thing. Okay, so I'm going to introduce their faculty, one of their faculty advisors, Ron Lasser, who's a professor of the practice in electrical and computer engineering, and he'll introduce the collaborators of the student team. So Ron has his Master's of Science, PhD, Bachelor of Science, all from Carnegie Mellon in mechanical engineering. So here's a guy who's already interdisciplinary. He's teaching electrical and computer engineering, but all his degrees are in mechanical engineering. He joined Tufts as a professor of the practice 7 years ago. And he has been teaching a number of courses and brought a lot of the project-based learning to the classroom. Has been responsible for modifying the junior design and senior design courses in the department, and he's been a great contributor to our first year experience discussion. So we're delighted to have Ron as a member of our faculty. He's also, most recently, was principal at Product Development Consulting, I guess, before you came here, and is still very actively involved in the consulting world while he's here at Tufts. And he has, I guess, your most recent patent is for a semi-automated medical device for products and methods for single parameter and multi-parameter phenotyping of cells. Is that correct? Okay. He also is a winner of a teaching award, so we're really pleased to have Ron, and I'll let you introduce the rest of the team, okay?
Thank you very much, Linda. So this project came about by me going to the ophthalmologist one day and just starting a conversation. So I'd like to, before I start talking about the project, I'd like to introduce the sponsor, which is Dr. Ferrentino, who is a jumbo himself, so he's an alum to at least 2 people in the audience. We chatted about one of the biggest problems relative to ophthalmology is in his practice. And one of that is identifying what glaucoma is and then doing triage on it based on what needs to be done. And he started telling me that the technology was still in the 1950s. And so the first thing we did was we went and looked at one that he happened to have on the shelf from the 1950s. And there were tubes in it, and it was really interesting to go into those schematics and to figure out what did they do to make this measurement. And that took about a good semester of work to understand that. Subsequent to that, we found out that we understood what the measurement they were making, but it was kind of behind the times since it was from the 1950s. And we thought that we could do this a lot more effectively rather than analog. We could do this in the digital realm. So at that point, I tried to recruit some ECE students as part of their capstone senior design project to take this project on and to come up with a working design. And so we had 5 people join the team. Hassan Oukacha and Mical Nobel are here today to do the presentation. 3 members of the team are not here due to work and family related issues. One is Nick Ferrentino, who's out in Wisconsin. Denise Nguyen, who is out in who is on personal business, and then Bianka Mejia, who due to work related could not make it today. But with the first 4 were electrical and computer engineers, and Bianka was an engineering psychologist doing human factors. And so there's a lot of engineering that had to go on to try to understand this. But there was also a lot of human factors and man-machine interfaces that was really important. There's several different stakeholders. There's the stakeholder being the patient and having this device placed on their eye. There's the stakeholder of the doctor who needs to get reliable results and be able to use this. There's the technician who actually needs to conduct the tests and understand something. And then there's the flow through the ophthalmologist's office of how you use this, how you show the data, and how it's to be used. And so all those dimensions had to be taken into account through this design. So I'm going to let the students tell you the details. And then at the end, maybe there'll be some questions that Dr. Latina can answer specifically about glaucoma. But rather than do that right now, I think once we educate ourselves on glaucoma and what they did, the questions will be more forthcoming. One other person to mention, and that's Professor of Practice Dan Hannon, who's sitting in the third row over there, who was also the other advisor on this project, and worked on it from the human factors engineering psychology perspective. So, Hassan Oukacha.
Is it working?
Here we go.
Okay.
Do you
All
want the
right.
lights on or off?
Well, I guess that's up to you guys. Can you see okay?
Off?
Lower them a little bit.
Okay. Well. How's that?
It's better?
No.
No?
Okay, well.
Either one.
There we go.
There you go.
Perfect. Okay. All right. Hi everyone. I'm Mical Nobel. Thank you for coming out today. We're really excited to be here and to be receiving the Ricci Prize and to tell you about our product. I graduated last year with a BS in computer engineering, and I'm currently working at Athena Health over in Watertown as a software developer. It's a healthcare IT company, so it's sort of the same vein.
Hi, everyone. My name is Hassan Oukacha. I graduated last year from Tufts in electrical engineering department, and I'm pursuing my master's degree here at Tufts for electrical engineering as well. So Mical and I are here to represent our team and to tell you about our project last year, which was digital tonographer, which is a device that we're hoping to prevent a patient from getting glaucoma using this digital device. So this is, in our presentation, we'll start our presentation by defining the glaucoma, its treatment, and we'll walk you through the operation of the tonometry as well as the tonography, and we mentioned the difference between these two devices. We will talk about the mission, our mission statement, and what we're focused on in our project. And we'll show you the circuitry of our device, and we'll have all the specification of our device as well. And we'll end our presentation by a short demo, and we'll open it to Q&A.
Okay, so what exactly is glaucoma? Glaucoma is a group of eye diseases that cause damage of the nerve at the back of the eye, which is called the optic nerve. The optic nerve is a bundle of nerve fibers that carries information from the eye to the brain. Damage to the optic nerve can lead to vision loss and, if left untreated, eventually, potentially, total blindness. Glaucoma is correlated with high fluid pressure in the eye. Fluid in the eye is called aqueous humor. This fluid serves to nourish the area around the colored iris and behind the cornea, and to help it exerts pressure to help maintain the eye's shape. Aqueous humor is continuously produced within the front of the eye, and it causes that pressure that's called intraocular pressure, or IOP for short. To maintain the IOP, the fluid drains out between the iris and the cornea. So you can generally think of glaucoma as a sort of plumbing issue, which clogs that drainage pathway. So basically, like, if that's clogged, then obviously the pressure is going to be building, and that is what causes the stress on the eye that on the optic nerve that leads to the vision loss. Proper and accurate measurement of IOP can help lead doctors to early diagnosis of glaucoma. It can also help with the selection of the best treatment options to mediate the patient's condition. Glaucoma has often been called the silent thief of sight because the loss of vision occurs gradually over a long period of time, and most patients experience no symptoms at all. Some of them don't even know if they have the disease until irreversible damage has been done. This is why it is so important for us to be able to catch it early and to diagnose it early, because that gives the doctor more time to prevent any unnecessary damage.
So while working on this project, we came across some statistics and facts that shocked us really, and would like to share some of them with you. So there are actually 3 million Americans living with glaucoma, and half of this 3 million don't know about their condition. So they are not aware if they have a glaucoma or not. And almost like 120,000 Americans lose their vision because of this illness. So it's a disease there that we have to prevent, or at least to reduce the rate of it. So, and approximately 10% of people with glaucoma who receive proper treatments there reduce their vision or experience loss of vision along the way. And while older people they are at higher risk, everybody is exposed at any age to this disease.
Perhaps the most widely used method for doctors determining the IOP is a procedure called tonography, which measures the force necessary to apply on a constant area of your cornea. Most tonometers are calibrated to measure pressure in millimeters of mercury. There are different kinds of tonometer devices, which you can group into two categories, contact and non-contact. We will quickly describe to you 3 methods, the first 2 of which are contact. And just remember that during most of these methods, doctors typically give you eye drops, so don't get too freaked out because it's uncomfortable, but it's not that uncomfortable. So the first commonly used mechanical tonometer was designed and introduced by a man named Schiatz in the 1900s, early 1900s. And this instrument was simple, easy to use, and relatively precise, and it was pretty revolutionary and revealed a lot of information about glaucoma that we didn't know before. It was quickly accepted, and the way that it works is it has a plunger that is used to gently push on your cornea. And then Hans Goldmann introduced an adjustment for ocular rigidity in this tonometer in the 1950s. Ocular rigidity being basically it is an effect of your your eyeball's shape and firmness, and that has an effect on the way that you. It basically led to sources of error when it wasn't accounted for in the original tonometer. So this has actually become known as sort of the golden standard of tonometry. It also was a little bit more gentle than the Schiatz tonometer. And then today we have.
You may or may not experience the EPOF test if you go to eye doctor, but what it is, it's a non-contact tonometer, and the way it works, it uses EPOF to send the air to your cornea, to your surface area cornea, and after receiving the light, so that's the force that's applied, and that's how it measures the intraocular pressure. It's not that accurate, although it's very expensive. So that's but it doesn't require any expertise to use it. That's why it's commonly used in doctor's office, and it's a simple way to check the intraocular pressure since it's quick and painless. That's why we find it everywhere.
So why is this test not enough? Well, tonometry only takes a static measurement of IOP. This does not give us the information on the rate of aqueous outflow, which is a more accurate assessment of the condition of your eye and how at risk you are for glaucoma. While these static measurements of IOP are good indicators, they are not as accurate as continuous measurements could be. Tonometers are also inherently imprecise, although today's have improved from their original. Generally, ablation techniques like Goldman's have totally replaced the indentation technique represented by the Schiot's instrument that I described earlier. This is primarily because the Goldman reading can be taken with little disturbance to the eye, unlike the heavy weight and corneal indentation associated with the Schiot's tonometer, which causes actually a noticeable increase in the pressure of the eye during the assessment, unlike the Goldman tonometer. But actually, one aspect of this raised IOP during the Schiot's tonometry test still makes it more advantageous compared to even today's tonometers, which is that it is able to make an estimate of aqueous outflow by a test called tonography. Tonography is a clinical test that was introduced by Grant in 1950. Grant showed that a continuous recording from an electronic Schiot's tonometer could be analyzed to give estimates of aqueous outflow and the rate of aqueous flow. Grant recorded the output of an electronic tonometer on a strip chart recorder, which is essentially just a roll of paper with a printout of a graph on it. And he showed that this data, combined with specific tonometer calibration, with a specific tonometer calibration scale, could actually be used to provide a quantitative expression relating the outflow of aqueous humor to the driving pressure. Grant calls this value the coefficient of aqueous outflow facility, which we labeled with the letter C. Grant's formula sets C equal to the change in the ocular volume occurring over time as a result of the difference between the average pressure during tonography and the resting pressure in the eye before application of the tonometer.
So right now we are talking about the problems encountered using this corner tonographer. As we said earlier, the tonographers are outdated, so they are from the 50s or 60s, and most of the parts, the replacement parts, are impossible, or it's really hard or impossible to get. So if you are out of something, so you cannot find it elsewhere. A perfect example, this tonographer, they use a roll of paper as a user interface, and if you are out of that roll of paper, it's just the device is not functioning anymore because you cannot substitute it. And most of the patients, they got really scared when they see how huge that tonographer and how outdated and rusty is, and especially if they got really scared if they know that that device will be sitting on top of their eye. So it's not the best experience out there. And what makes things worse is the length of the processes of the measurement process. It takes about 2 to 4 minutes, which is really uncomfortable to do. Now we talk about disadvantage of tonographer. So we can ask yourself why we care about these devices. There is a lot of disadvantage of it. Well, the answer to the question is this is the only device that measures the pressure inside the eye, or the eye pressure, and track it over time. So by doing that, the ophthalmologists, they have a better idea of the behavior of the eye for extended period of time, and this will allow them to prescribe the right treatment for the patient, either surgery or medication or any other method. And as opposed to tonometer, the tonographer gives a better result and more accurate result.
So, learning this information helped us clarify the problem that we wanted to tackle. Essentially, we know that glaucoma can be managed through a number of methods, like different types of surgery and medication. And measuring the IOP, or intraocular pressure, is a great way to do this. But there are definite benefits to be gained from getting the more direct information on the patient's aqueous outflow, especially for assessing how effective glaucoma treatments are. However, the only tool that can do this is totally outdated. It's not up to the standards of our modern technology. This brings us to our mission. which is to assist in the prevention of glaucoma by creating a digital and perhaps an eventually standardizable device that can better assess the damage of the optic nerve in its early stages. We hope to enable ophthalmologists to get an accurate measurement in a shorter period of time, with a maximum goal of 2 minutes. This should ease the burden on the doctor and medical staff and provide a more pleasant experience for the patient without compromising the accuracy of the results and perhaps even improving it. So we can boil down the key contributions of our device into the following components. 1, automating the calculations from the tonographer. Originally, the doctor had to perform intense hand calculations on those printout graphs that we told you about earlier. Obviously, we are capable of doing better than that now. 2, displaying all relevant information clearly and concisely to the user. 3, enabling the measurement of the effectiveness of new FDA-approved drugs targeted to increase outflow facility. 4, improved ability to select the best medication for the patient. And 5, to reduce invasiveness by minimizing the length of test duration.
Right. So for our vision at the beginning of our senior year was clear. So we wanna work on a medical device, and we wanna use the software and hardware skills that we get here at Tufts toward something that's touchable and that's tangible to the people. And so we, after contacting Dr. Latina, he gave us a bunch of ideas about the project that we may work on. And after seeing the needs and reading literature about tonography and its perspective, we choose this project to work on. So the first step that we took was to visit Dr. Alatina's office, talk to him and his staff, and see what their needs are and the specification that they want. We also give them a questionnaire that they fill out. So in order to narrow down this specification to a tangible goals that we can transfer to pre-sales and management tasks. So that was done in our first semester, which ended by designing a prototype, or it's not a prototype, by designing a schematic of our circuit. And for the second semester, we started working on the circuitry and building the circuit itself, which took a long time. And we end up by finding the usability testing. The hardware of the device, the hardware of the device itself, it consists of a probe, which is 2 coils that are on top of each other, and the rod that depending on displacement of the eye, can go up and down. And by connecting a voltage that has like 60 gigahertz frequency, it creates a magnetic field that, based on the displacement of the rod, it will take that magnetic field and create a voltage in the up coil. So that was the voltage that the probe measures. And since we have a really very weak signal or weak voltage, we create a circuitry that amplify it. So we use a bunch of buffers and amplifier to get the signal to the gain that we want, or to the level that we want. And also our circuitry takes reduce the noise or minimize the noise that we had. So for after this circuit, the output that we got is a DC, so we convert from AC to DC. It's about, it ranges from 0.5 to 3 volts. That DC we feed it to our Arduino, which plays 2 roles. So we use it as a analog to digital converter to get the digital, to digitize our signal. This digitized signal, we send it over XP to the processing unit in our computer, where it got processed and displayed on the screen.
So basically, this is here we'll show you kind of the stages. So here you can see this is actually what the original device looks like. There you can see that's the scale that shows the voltage reading. It's obviously this looks very analog. I mean, the other half of this is the printout. That cable actually is connected to the probe itself that gets put on your eye, and so that really limits the range of motion for the doctor, which, you know, that was a big consideration when we were looking at this, and we were like, well, if we could make this wireless, like that would obviously really help the doctor be more comfortable when they are using this device. We then moved on to this. This is actually the reconstruction of that circuit on a breadboard. Hassan and our other teammate Nick spent a lot of time working on this and got help from Warren to really understand this and kind of figure out how it's working so that we could make our adjustments and feed it to the Arduino, which was basically this next step. This is our final product, which you can see up here. Here we have that same circuit, which is the amplification circuit, taking in the signal from the sensor, which is on the left. That's the probe. This is the probe. And basically it gets fed into the amplification circuit, which we really made a lot more compact. And then we feed it from there to the Arduino that is fitted with the XB. The Arduino converts the signal from analog to digital and then sends it through the XB over to the computer. So in rethinking about the user interface, Bianka, our human factors engineer, helped us clarify what usability issues already lay in the original device and how you could go about fixing them. There are some obvious limitations that Dr. Latina, our project sponsor and active ophthalmologist, helped us kind of figure out. Well, one example that we just said is this whole making it wireless thing. That also helps. It also helps the doctor be more comfortable. But that's something to consider when we're making the actual other part of the user interface, being the computer that we are recording the information on. Dr. Latina made it very clear that he wanted the information that we were seeing in analog to be displayed in digital on the computer, and that is what we did. So what we need to do first of all is we need to be able to receive the wireless information, interpret it, and then display it in a much more appealing and logical way than it was originally. We also decided to so what we did is first we just sort of transplanted what was originally there, being the live updated graph, and we put that on the screen. We got that to be transferred over. And then we added additional functionality just to make it, even more, to help for more improved experiences. And so what we did, for example, is that we automated the calculations that are made. And what we have actually that you will see eventually in the demo is that we have it so that when you can pick sort of a 2-minute window that you want to analyze, and then it automatically calculates for the IOP and the aqueous outflow just for that subset, and then you can save that record, which is another thing that we added just so that you can maintain all the results from these different exams, including the images of the graph, all in one place. We wanted it to be simple and logical enough that any member of the medical staff could help in this procedure, and it wasn't all on the doctor. So in creating the new interface, the user interface was implemented using the programming language Python, which was applied to create a WX Python interface. WX Python is a toolkit that allows Python programmers to create highly functional graphical user interfaces. The software reads in the raw data through a serial port at 10 Hertz, and then it finds a sample average for all the readings found in 1 second in order to reduce the error from any noise. we believe that the data that we're plotting is actually more accurate than the raw data, which is what the data on the printout would have been, because what we are plotting is the sample averages and is hopefully a little bit more noise-free. So this was the original prototype, I guess, for the user interface. This is our first step. So we go here. Okay, it says QuickTime not available. So anyways, it was much more simple than this, which is closer to our final product. Bianka helped us in kind of designing this in a way that would look good and like make sense for the user, be easy to read. And so what we have here is we have a big graph in the middle, which is, like what was available to the doctors before. And then on the top left, you have the name and date of birth, which actually in the complete version, you can like add a new patient and then save it, or you can load it and then you can load the patient again, and that is how we save the records all to the same place. And then on the top right is where we have the information regarding the IOP and the aqueous outflow, which in the complete version that you'll see in the demo, really when you decide to like save the record, you go to a certain window and then it automatically calculates based on that window. And also this data is not accurate, it's simulation data, and that is why it looks kind of crazy. Your eye doesn't really do that.
Well, as any project on this site, our team faced many challenges. So when we started this project, we got overwhelmed by the complexity of it. There are many components, there's software, hardware, a user interface, patient comfort, and also the robustness of your design, since it'll be touching the eye, and we don't want anything to go wrong at that stage. And the first problem that we encounter is how to connect the circuit sensor to user interface. So we want something that will be easier for the doctor, for users, and also for the patient to view it, and also to save their records to a nice, easy to navigate platform. The major issue, or the other issue that we face, is since the device was outdated, was like in its 1950 or 1960 technology. So we found that many of the components that was in the device, it's really hard to find literature about it or to see any matching component in the new technology. So lucky we were that we found Warren, who was our lab technician or engineer, who helped us a lot, and he gave us all the need that we need at that time. Also, learning Python itself, since it's new language, we never use it, so it took us like a couple of weeks to master the language, because it is the language that we use to create our user interface. The biggest problem that we had, or biggest challenge, is the Bluetooth, or how to transfer the data from our circuit to the processing unit in the computer. So that took us like probably about 3 weeks. We start with the Bluetooth technology, since it's widely used in medical device and it's well documented technology. But the problem, we had some issues with it. Somehow we have to ping it and in the first place to start receiving the signal, which was not the result that we were looking for. After spending that time working on Bluetooth, we switched to XP, which is also wireless communication technology, and it's give us the right result. So also we faced the challenge of connecting the serial port in our device. For future direction, our design or our device laid the foundation for many improvements that can be done. This design could be improved by improving or redesign the probe itself, and figuring out how we can, instead of the coil or that probe right there, we can use either capacitor or capacitive sensor or inductive. We didn't have time to look into that. The other thing that we could have done is to design PCB, which didn't have the time to do is, but it could be done easily. And or we can also, it can be designed using a CMOS technology chip, which is gonna save a lot of power, make a device much smaller, and reduce the time. And so continue development on user interface.
The user interface currently satisfies the initial goal of getting the information displayed on a screen, automating the calculations, and additionally it provides a simple record that is maintained for each patient. However, with increased experience in software development, we feel like this is just the groundwork, you know. We have plans to improve the current functionality of the interface, which could include more customizability on the user's end, as well as custom reporting on the results. And one potential goal actually that we talked about was to be able to control the device or certain aspects of the device from the user interface, maybe to go along with a new probe. For example, like pre-test calibration, if we could hit like a start and stop button that from the user interface, and like any technician or really anybody could do it. So that would be great.
So for the impact on our sponsor,
Basically, just overall, we we have a product that we feel is vastly improved, and we're very excited to continue working on this project towards the future and all the future directions that we just mentioned. So, thank you.
all credit goes to Nicola, Ferrentino, and Bianka Mejia, Denise, who could not attend this event. And special thanks to Warren, our lab technician, and Tolga, who's a senior now. I don't know if he's here now, probably not. And Dr. Latina, Dr. Lasser, and Chris Owens, who graduated 2 years ago to work on this project.
Thank you. Finally, we'll just give you a quick demo.
Yeah.
Okay, so this should already be working. So basically, all right, so we're running the program. All right, here we see there is a folder. Select your entry for patient record. I made one. It's called patient journal. Here we go. New patient.
Need a volunteer.
We need a volunteer who wants to be our patient.
Hey, how's it?
There we go.
We just need, thank you, come up. So, please state your name for everybody. All right. Steve.
I hope this is HIPAA compliant.
That's the next step. All right, so date of birth.
We can get a
Let's
fake one,
just
yeah.
say
Make it up.
1985. Okay, go. All right, so theoretically, this device would now be on your eye, but if you could please just come over here and press up on this
Oh, this is the better
for
one.
us.
I think that's a good idea.
All right, and now I will hit resume. There you go. So if you put it down now, you will see that it
If
drops.
you look on the screen. see
And
it's-
now?
okay.
See, it steadies down, and then there we go. Okay, so theoretically, this test would last for, sorry, hold on. This test would last for about 2 minutes, but we'll just cut it short. So now we'll go into snapshot mode, which is where you save the record. So let's just say record snapshot. If you go here, you see that this has now calculated the IOP and aqueous facility from, or this is actually C, aqueous facility is C. And so if you, theoretically, if this were like a longer test, then we could move this and it would calculate the different results based on the window that you were seeing, but this is the only data we have, so this is the calculation that we will use. So let's say record snapshot, just save this. Yes, we want to save this data. Let's just say inverted, black and white, color effects. Okay, so now it's saved here. So if we go over here to the patient directory, refresh. Here we go. So you see that we have a new patient. And you can see that here, the image was saved of the graph. And the record, the data was saved to this record, where there is, this is just one form of the record, but then we also have, and like every time that you have another examination, the data will be added. And so, all right, if we go to here, this is where it all gets stored, except for right now the image link isn't working. But anyways, so basically you eventually get a table like that. I can show you a more filled out record. Let's see. There we go. See, this is like, every time there's another examination saved, we keep the date of examination over there, and then the IOP, aqueous facility, and the image, which will eventually show up there. And so that is what we got.
We should open for questions.
Any questions?
I just want to congratulate you, and then you can take questions. Because you did a great job.
Yeah.
It's a very important project, actually. And as you said, there is really, I brought in this like 50-pound instrument, which is heavy steel and this vacuum tubes, and gave it to Ron and said, here, can you figure it? He said, can you figure this out? Luckily he knew vacuum tubes. And so age has its advantages. But one of the issues, as you clearly mentioned, was that we're actually developing a whole set of new drugs for glaucoma. And those drugs are actually designed to improve what we call the outflow of the eye, the outflow facility. But this is the only technology that you can actually measure the outflow facility. And it was, as we saw, very old. So when I actually presented this at one of the major meetings, and we actually got like 4 companies right away who came up to me, but are very interested in getting the product once it's set to go, because this will be the only way of actually determining those, how the drugs are actually acting, how effective they are, and also when we follow the patients, as you saw, by having serial tests, we can be able to see how well the patients are doing with the medications. So it's got a great importance. So congratulations. And
One other announcement, obviously everybody, this project is not completed, as you can tell. So if everybody would like to continue working on it, they can contact me.
any other questions?
No questions?
I have one general one. First of all, I'm very impressed as a learning experience because projects in the real world touch a lot of dirty things, not in cyberspace. And, but how did you find, it's got to have been a massive project to tackle senior year. Was it bigger than your expectations? Was it more than 500 tackling?
It was much bigger than
I would say it was very big, but I think we figured that out early on. And we just wanted to get as much as we could, figure out, or at least make progress enough on as much as we could to leave it in a better place for the next
So start this project like by trying to redesign the device itself, including the probe. And we say that it's a huge project and we cannot tackle everything. We cannot do the user interface, the hardware of the circuit itself, and the probe. So that's why we decided to go, since the probe is working fine, we decided to use it for this device, replace the circuits, and do the user interface.
One other point, and both Mical and Hassan have been kind to mention that the Bluetooth didn't work, and there were a lot of false starts along the way, and there were a lot of glitches along the way, and so the team had to recover. There were many conversations in my office that, what we do now. And so I think they got a lot of real-world experience trying to lead their way through the minefield to actually get this working. So there's a lot of stuff that is not being talked about because of all the failure, restart failure, whatever, but it was their determination that really pushed us forward.
That's the learning experience. Very well done.
I think I don't want to lose our audience, and so is there any other questions, or? So I want to just make sure that we, I can thank Steve and Geraldine again so much for making this prize possible and the lecture possible. And Steve has a little background. He's a Tufts mechanical engineering alum from, we won't say what class then, 2000. He has an MBA from Harvard Business School, and he's currently a member of our board of advisors, and he's involved in our curriculum development task force as well. So Steve is giving in many ways, and so we're very grateful to him. And I thought maybe you guys could come up and we could give you an official certificate. You already got the prize money, right? But you sure you don't want to? So maybe we take. I guess we're taking a video, so at least I can say congratulations to Mical.
Thank you.
And congratulations to
Thank you.
Awesome.
and I don't
Great
know.
job.
Thank
Hard
you.
to do.
Thank you,
I'm doing my best.
Yes.
Well done.
So